For 4.5 billion years, the Sun has spent millions of tons of mass every second, and still, its light has never failed. Beneath the calm golden surface, gravity presses inward, fusion pushes outward, and a nearly perfect balance keeps the star alive. Every ray crossing space begins in a core where hydrogen waits for ages before a rare nuclear reaction releases its energy. The Sun shines not because its fuel burns quickly, but because nature has made fusion astonishingly difficult. A like subscription or share helps more quiet science journeys reach others who enjoy learning at a slower pace. Gratitude goes to everyone spending part of the day or night here. A comment can also share the local time and the place from which this story is being heard. Now the light can be followed backward from Earth, through the Sun's restless surface, and into the ancient furnace that has endured since the solar system began. Long before the Sun becomes a familiar disk in the sky, it begins as part of something far colder, darker, and more diffuse. A vast cloud of gas and dust drifts through the Milky Way, carrying mostly hydrogen, some helium, and a thin scattering of heavier elements forged inside older stars. Its material is spread across distances far greater than the present solar system. For a time, gravity works quietly. Each atom attracts every other atom, yet the cloud can resist collapse through internal motion, turbulence, magnetic fields, and the pressure of its own slight warmth. The cloud changes over immense stretches of time, disturbed by passing stars, shock waves, and the slow rearrangement of matter within the galaxy. At some point, one region becomes a little denser than its surroundings. That small difference matters. Greater density creates stronger gravity, and stronger gravity draws in more material. As more material falls inward, the region grows heavier, denser, and more difficult to stop. A process begins in which collapse feeds further collapse, and the future Sun starts to separate from the darkness around it. The forming object is not yet a star. It is a protostar, a young concentration of matter whose center is growing hotter under its own increasing weight. Gas falls inward from all directions, but it does not fall cleanly. The original cloud carries some rotation, however slight, and as the cloud contracts, that rotation becomes faster. The same principle that makes a spinning figure turn more rapidly when pulling inward also shapes the birth of the solar system. Material flattens into a broad rotating disk around the central protostar. Within that disk, grains collide, clump, and begin the long path toward planets, moons, asteroids, and comets. At the center, most of the available mass gathers into one object. The Sun eventually contains nearly all the matter in the solar system, and that dominance is already being established during collapse. The planets remain fragments orbiting a central mass that outweighs them altogether. As the protostar contracts, gravity converts motion into heat. Falling gas speeds up, collides, and transfers energy through the deepening interior. The center becomes denser, and the pressure rises. This heating does not come from fire in the ordinary sense. There is no burning wood, no oxygen-fed flame, and no chemical reaction capable of sustaining a star. Chemical energy is far too weak. Even if the young Sun had been made from a fuel that could burn in a familiar way, it would have exhausted that energy in a tiny fraction of its present age. The fact that the Sun has shone for billions of years requires a source far deeper than chemistry. Yet that source does not begin immediately. Before nuclear fusion starts, the protostar shines mainly because it is contracting. Gravity itself provides the energy. The young Sun is already luminous, but it has not yet reached the stable condition that will define most of its life. The contraction continues because nothing inside the protostar can yet fully balance the inward pull of gravity. Every layer presses on the layers below it. Near the center, the accumulated weight becomes enormous. Matter behaves in ways unfamiliar at ordinary temperatures. Atoms collide with growing violence. Electrons no longer remain neatly attached to individual nuclei, and the interior becomes a plasma, a fluid of charged particles moving through intense heat and pressure. Still, the central temperature must climb much higher before hydrogen fusion can proceed at a rate sufficient to support the star. Gravity is trying to compress the protostar into a smaller and denser body, while heat is building an outward pressure that resists the collapse. For a time, gravity remains stronger. The star contracts, the center heats further, and the conditions move closer to the threshold where the nature of the energy source changes. Hydrogen nuclei are protons, and protons carry positive electric charge. Because like charges repel, two protons do not naturally join when they approach one another. They push apart. In the core of the forming sun, however, the temperature becomes so high that protons move at extraordinary speeds. The pressure becomes so great that vast numbers of them are crowded into a small volume. Most encounters still end in repulsion. The particles approach, slow under the electric force between them, and separate again. But the core contains so many protons, and their encounters occur so often, that rare events become important. Quantum physics allows a small number of protons to cross the barrier that classical motion would not overcome. Once they come sufficiently close, the strong nuclear force can bind them. This is the beginning of the chain of reactions that turns hydrogen into helium. The ignition of fusion is not an explosion in the usual sense. It is a gradual transition. As the center grows hotter, nuclear reactions become more frequent. Each successful sequence releases energy, and that energy adds to the pressure inside the protostar. The new source of heat slows the contraction. Eventually, the outward pressure generated by the hot interior becomes strong enough to balance the inward force of gravity. At that point, the young sun enters the long, stable phase of its existence. It becomes a main sequence star, one that shines by converting hydrogen into helium in its core. The birth cloud has produced a self-regulating sphere of plasma whose structure is maintained by a balance between two opposing tendencies. Gravity holds the sun together and creates the pressure needed for fusion, while fusion provides the energy that prevents gravity from crushing the star further. This balance is the reason the sun does not blaze through its fuel in a brief and violent flash. The star is not a bomb with all its fuel reacting at once. Fusion occurs only where the temperature and density are high enough, mainly in the central region. Even there, the reactions proceed slowly on the scale of individual particles. A proton in the solar core may wait an immense span of time before taking part in the first step of the fusion chain. The sun's brightness comes not from each reaction happening quickly, but from the unimaginable number of particles available. Tiny releases of energy, repeated across a vast core and sustained over billions of years, produce the steady power that leaves the surface as light and heat. The newborn sun does not immediately resemble its present form. It passes through periods of stronger activity, continuing adjustment and interaction with the surrounding disk. Powerful radiation and streams of charged particles sweep through the young solar system, clearing away much of the remaining gas. The planets continue to form from the material left behind. Close to the sun, heat favors rock and metal. Farther out, colder conditions allow ices and gases to remain. The central star becomes the organizer of the entire system through mass, gravity, radiation, and time. Its light sets temperatures, its gravity defines orbits, its magnetic activity shapes the space between worlds. Every planet begins its history under the influence of a star that has only recently learned how to hold itself in balance. The age of the Sun, about 4.5 billion years, is therefore not the age of a flame that has somehow avoided going out. It is the age of a gravitational structure sustained by nuclear physics. The Sun shines because its birth placed an enormous amount of hydrogen beneath an enormous amount of weight. Gravity created the pressure. Pressure created the heat, and heat allowed fusion to begin. Once fusion began, it didn't remove gravity from the story. It completed a cycle in which gravity and nuclear energy regulate one another. If the core produces slightly less energy, gravity compresses it, raising the temperature and increasing the fusion rate. If the core produces slightly more energy, the interior expands, cools, and slows the reactions. The same force that threatened collapse becomes part of the mechanism that preserves stability. From the outside, the result appears simple. A bright sphere rises, crosses the sky, and sets. Beneath that calm appearance lies the memory of a collapsing cloud, a disk of forming worlds, and a central furnace that turns the lightest element into something heavier. The Sun has been shining for almost the entire history of Earth, because it began with enough mass to ignite fusion, but not so much mass that it would consume its fuel in a short and furious life. Its birth places it in a range where endurance is possible. The ancient cloud does not merely create a star, it creates a star capable of remaining stable long enough for planets to cool, oceans to gather, atmospheres to change, and life to emerge. The first answer to the mystery of the Sun's longevity is therefore hidden in its beginning: a slow collapse, a rising pressure, and the quiet moment when darkness becomes a furnace. The Sun appears calm because its surface is distant, but its interior exists under the burden of almost unimaginable weight. Every layer of solar material presses on the layers beneath it, and the deeper the descent, the greater that pressure becomes. Near the center, the gas is compressed by the mass of nearly the entire star above it. The result is a structure in which pressure rises steadily toward the core, creating conditions that no ordinary furnace on Earth can reproduce. Gravity does not merely hold the Sun together, it shapes the temperature, density, and behavior of the matter inside it, turning a vast sphere of hydrogen into a place where nuclear reactions become possible. At the surface, the solar gas is thin enough for light to escape. Deeper down, particles are packed more closely, collisions become more frequent, and the pressure climbs through layer after layer. By the time the center is reached, the pressure is hundreds of billions of times greater than the atmospheric pressure at Earth's surface. The temperature rises to roughly 15 million degrees Celsius, while the density becomes many times greater than that of water. Under such conditions, matter no longer behaves like the familiar gases found in air. Atoms cannot remain intact. Electrons are stripped away from their nuclei, leaving a plasma of freely moving charged particles. Hydrogen becomes a sea of protons and electrons, crowded together and driven into constant motion by extreme heat. The core is not solid, yet it resists compression through the pressure created by those moving particles and by the radiation trapped within the star. This resistance is essential, because gravity is always trying to pull the Sun into a smaller volume. The pressure at any depth must be strong enough to support the weight above it. A layer that cannot provide enough support begins to sink. As it sinks, it becomes compressed and hotter. Its pressure then rises until it can again help carry the overlying mass. The Sun therefore arranges itself naturally, with the highest pressure and temperature at the center and lower values toward the surface. The central conditions are severe because the Sun is massive, but its mass also falls within a range that allows long stability. A much smaller object cannot compress its center enough to sustain ordinary hydrogen fusion. Such an object may glow for a time from contraction, but it never becomes a star like the Sun. A much more massive star creates far higher core temperatures and burns through its nuclear fuel at a much faster rate. The Sun lies between those extremes. It is heavy enough to ignite hydrogen, yet moderate enough to consume that hydrogen slowly. Its longevity begins with this balance between sufficient weight and restrained intensity. The connection between pressure and heat follows from the motion of particles. Temperature measures, in broad terms, how energetically particles move. When gravity compresses the solar interior, particles are forced into a smaller space. They collide more often, and the energy of their motion rises. Compression therefore heats the core. This same process operates during the Sun's formation, when falling gas converts gravitational energy into heat, and it continues to shape the mature star. The core remains hot because gravity maintains the compression, and because fusion adds a steady supply of energy. Gravity establishes the conditions, while fusion helps preserve them. The Sun's center is often described as a furnace, but the comparison is limited. A furnace burns fuel through chemical reactions involving electrons in atoms. The solar core operates at a deeper level, where atomic nuclei interact. Chemical flames require temperatures far below those of the Sun and release only a tiny fraction of the energy available from nuclear reactions. The core is also sealed beneath a vast envelope of plasma. Energy cannot leave it quickly. Light produced near the center is repeatedly absorbed, scattered, and re-emitted as it attempts to move outward. This trapped radiation contributes to the internal pressure, adding another outward force against gravity. The pressure inside the Sun therefore comes from more than one source. The fast motion of particles creates gas pressure, and the intense field of photons creates radiation pressure. In a star of the Sun's mass, gas pressure plays the larger role through much of the interior, while radiation still contributes. In heavier stars, radiation pressure becomes more dominant, and the balance grows more delicate. The weight of the Sun also explains why fusion is confined to the core. Hydrogen exists throughout the star, but only the central region is compressed and heated enough for nuclei to approach closely enough, often enough, for fusion to proceed at a meaningful rate. Farther from the center, the temperature and density fall. The material remains hot plasma, but the collisions lack the necessary conditions. The Sun is therefore not burning everywhere. Most of its volume acts as an envelope around a relatively small energy-producing center. If the entire Sun fused hydrogen at once, its life would be drastically shorter. Instead, only the deepest portion participates directly in the main sequence of nuclear reactions. Even within that region, fusion is remarkably slow for each individual proton. The central pressure forces particles close together, but electric repulsion still prevents most encounters from leading to fusion. The strong nuclear force can bind protons only at extremely short distances. Most protons collide, repel one another, and separate. Rarely. Quantum behavior allows a reaction to begin. The rarity of that first step acts as a brake on the entire process. The Sun contains so many particles that the combined energy output remains enormous, yet the reaction rate stays slow enough to continue over billions of years. The same crushing pressure that makes fusion possible does not make it uncontrollably fast. Instead, pressure creates a crowded environment in which rare nuclear events occur steadily across an immense population of particles. The core's temperature is equally important because it determines how rapidly those particles move and how often they reach the narrow conditions needed for fusion. If the core were cooler, the reaction rate would fall. If it were hotter, the rate would rise sharply. This sensitivity helps create a natural form of regulation. A small increase in fusion warms the core and strengthens the outward pressure. The core expands slightly, reducing its density and temperature, which slows fusion. A small decrease in fusion allows gravity to compress the core, raising its density and temperature, which restores the reaction rate. The weight of the star, therefore, does not simply press downward without response. It participates in a feedback system that keeps the Sun near a stable condition. Gravity pushes inward, pressure pushes outward, and the core adjusts between them. This balance reaches through every layer. At each depth, the local pressure supports the material above. The deeper layers bear more weight and must provide more pressure. The outer layers bear less and remain cooler and thinner. The Sun's round shape follows from gravity pulling toward the center from all directions. Small distortions can arise from rotation, magnetic fields, and waves moving through the plasma. But the star remains nearly spherical because gravity acts so strongly over its great mass. The same inward pull that gives the Sun its shape also keeps its hot gas from dispersing into space. Without gravity, the plasma would expand outward and the star would dissolve. Without pressure, gravity would compress the Sun much further. Even the Sun's size reflects this compromise. Its radius is not fixed by a solid boundary, because the Sun has no solid surface. Instead, the size results from the point at which internal pressure and density fall enough for the outer layers to become transparent. Beneath that apparent surface, the plasma remains connected to the deeper structure shaped by gravity. Every bright patch in the photosphere rests above layers that ultimately depend on the central pressure. The light crossing space begins in a region where the weight of the star has forced matter into a state unlike anything in ordinary experience. That weight is not an obstacle to the Sun's shining, it is the cause of it. The Sun can remain luminous for billions of years because gravity has built a core hot enough for fusion, dense enough for steady reactions, and stable enough to avoid both rapid collapse and explosive expansion. Its mass presses inward without rest, and the interior answers with heat, motion, radiation, and nuclear energy. The quiet disk seen from Earth is therefore the visible expression of a pressure system extending all the way to the center. Beneath the sunlight lies the weight of a star, and beneath that weight lies the condition that allows the long burning age of the Sun to continue. The Sun survives because two vast tendencies oppose one another at every depth. Gravity pulls all of its matter inward, toward the center, while pressure pushes outward from the hot and crowded interior. Neither force wins completely. Instead, the star settles into a condition called hydrostatic equilibrium, a balance in which each layer supports the weight of the layers above it. This balance does not mean the Sun is motionless. Plasma flows, waves travel, magnetic fields twist, and the core steadily changes its composition. Yet on the scale of the whole star, the inward pull of gravity and the outward push of pressure remain matched closely enough for the Sun to preserve nearly the same size for billions of years. The equilibrium begins with gravity. Every particle in the Sun attracts every other particle, but the combined effect can be treated as a pull toward the center. A shell of solar material near the surface feels the gravity of almost the entire star beneath it. A shell deeper inside carries less enclosed mass below, but it must also bear the enormous weight of everything above. At each level, pressure must increase inward so that the lower layers can support the upper ones. This creates a smooth rise in density, temperature, and pressure toward the core. If pressure were equal everywhere, the outer layers would fall inward. If pressure rose too sharply, the star would expand. The actual structure forms where the pressure gradient, the change in pressure from one depth to another, provides exactly the support required against gravity. The Sun has no solid beams, walls, or foundation. Its support comes from the motion of particles and the energy trapped among them. In the deep interior, nuclei and electrons move rapidly because the temperature is immense. Their collisions create gas pressure. Photons moving through the plasma also carry momentum and contribute radiation pressure. Together, these forms of pressure push outward. The pressure does not act like a single wind blowing from the center. It acts locally, from one layer to the next. A slightly deeper region has slightly greater pressure than the region above it, and that difference supports the weight between them. Across the entire star, countless local balances combine into one stable sphere. Hydrostatic equilibrium is therefore not a rigid stillness, but a continuous agreement between neighboring layers. This agreement is closely linked to fusion. The core produces energy because gravity has compressed it to extreme conditions. That energy heats the plasma and helps maintain the pressure that resists further compression. Fusion does not hold the sun up by blasting matter outward like an explosion. Its energy is absorbed and shared through the interior, increasing the random motion of particles and sustaining the pressure field. The sun remains bound because gravity is still strong, but it does not collapse because the hot interior pushes back. The balance is gentle enough that the star can adjust when disturbed. If the core begins to cool, the pressure weakens slightly. Gravity then compresses the core into a smaller volume. Compression raises the temperature and density, allowing fusion to accelerate. The increased energy restores pressure and slows the contraction. If the core becomes too hot and fusion speeds up, the stronger pressure makes the core expand. Expansion lowers the temperature and density, reducing the fusion rate. The pressure then settles back toward its previous level. This response is often described as a stellar thermostat, though no separate mechanism measures or controls the temperature. The regulation emerges naturally from the relationship between gravity, heat, pressure, and nuclear reaction rates. This feedback is one of the main reasons the sun does not destroy itself. Nuclear reactions are highly sensitive to temperature, so a star without an effective response could become unstable. In the sun, however, hotter conditions lead to expansion, and expansion leads to cooling. Cooler conditions lead to contraction, and contraction leads to heating. The star corrects small departures before they become catastrophic. The process is not instant, because the sun is enormous and information moves through it at finite speeds, but the overall adjustment remains effective over long periods. The balance can support small vibrations as well. The sun rings with pressure waves that pass through its interior, causing tiny motions at the surface. These oscillations allow scientists to study the hidden layers through heliosismology, the solar equivalent of using seismic waves to probe Earth. The observed patterns confirm that the sun is arranged in layers whose pressure, density, and temperature closely match the structure expected from hydrostatic equilibrium. The sun's stability also depends on the slow pace of its evolution. Fusion gradually turns hydrogen into helium in the core. Helium nuclei are heavier and alter the core's composition. Over time, the number of free particles contributing pressure changes, and the core slowly contracts under gravity. That contraction raises the temperature, which causes the fusion rate to increase. The sun therefore becomes gradually brighter as it ages. Hydrostatic equilibrium does not keep every property perfectly constant. Instead, it allows the star to move through a sequence of balanced states. Each state differs slightly from the one before, but the changes unfold so slowly that the sun remains stable across immense spans of time. This distinction matters. Stability is not the absence of change. It is change that proceeds without sudden collapse or runaway expansion. The sun today is not identical to the young sun. Its core contains more helium, its luminosity is greater, and its internal profile has shifted. Yet gravity and pressure continue to match at every depth. The star adapts as its fuel is transformed. The equilibrium persists because the core can contract and heat as the conditions evolve, maintaining the reactions needed to support the overlying mass. This long adjustment makes the Sun a durable object rather than a fixed one. The outer layers participate in the balance even though they do not produce significant nuclear energy. Energy rising from the core passes through them, heating the plasma and shaping its pressure. In the radiative region, photons gradually transport energy outward through repeated interactions. In the convective region, hotter material rises while cooler material sinks. These motions carry energy toward the surface, but they occur within the larger gravitational structure. Rising plasma expands and cools because the surrounding pressure decreases with height. Sinking plasma compresses and warms as it moves deeper. Convection therefore follows the same pressure pattern that supports the star. Even the visible surface marks a transition in this structure, not a solid edge. The gas becomes transparent enough for light to escape, while gravity continues to hold the atmosphere and corona close to the Sun. Hydrostatic equilibrium also explains why the Sun is not spreading rapidly into space. The particles in the interior move quickly, but most remain trapped by gravity and by collisions with surrounding plasma. Only in the extremely thin outer atmosphere can some particles escape as the solar wind. The steady loss is tiny compared with the Sun's total mass. The main body remains confined because the average outward pressure is balanced by the inward gravitational pull. At the same time, the equilibrium explains why the Sun is not shrinking rapidly. Before fusion begins, a protostar can shine by contraction, losing gravitational energy as it becomes smaller. Once sustained fusion starts, the new energy source maintains enough internal pressure to halt most of that contraction. The Sun reaches a long plateau in its life. Not because gravity stops acting, but because gravity is answered by pressure at every level. This balance can appear almost paradoxical. Gravity is the force that threatens to crush the Sun, yet without gravity there would be no core pressure, no fusion, and no star. Fusion is the process that resists collapse, yet without confinement by gravity, its energy would disperse the gas. Each side depends on the other. Gravity creates the furnace, and the furnace supports the weight that created it. The result is neither victory nor defeat, but endurance. Across billions of years, the Sun remains poised between collapse and expansion, changing slowly while preserving its form. Its light continues because the star does not merely contain fuel. It contains a balance that controls how that fuel is used. The deepest secret of its long life is not only the amount of hydrogen in its core, but the quiet physical arrangement that keeps the reactions measured. A cosmic struggle reaches stillness, and within that stillness the Sun continues to shine. At the centre of the Sun, the long endurance of starlight depends on a process that is both powerful and extraordinarily reluctant to begin. The core contains a dense plasma of hydrogen nuclei, mainly single protons, moving through temperatures of about 15 million degrees Celsius. They collide constantly, yet almost every encounter ends without fusion. Each proton carries a positive electric charge, and like charges repel. Long before two protons can touch, the electric force pushes them apart. Heat gives the particles speed, pressure crowds them together, and gravity ensures that collisions never cease. But none of those conditions alone guarantees a nuclear reaction. The Sun shines because a tiny fraction of encounters escape the ordinary rules of classical motion. Quantum physics allows particles to behave with a faint uncertainty in position, so there is a small chance that two protons can pass through the barrier that normally separates them. Once they reach an extremely short distance, the strong nuclear force takes over. This force is far stronger than electric repulsion at close range, but it acts only across the tiny scale of an atomic nucleus. The first step of solar fusion therefore resembles a locked door that almost never opens. The pressure of the entire star keeps particles gathering at the entrance, and over immense spans of time, a few pass through. When two protons finally come close enough to interact, they still cannot simply remain as a stable pair of protons. One of them must transform. Through the weak nuclear force, one proton changes into a neutron, producing a nucleus called deuterium, a heavy form of hydrogen containing one proton and one neutron. The change also releases a positron, the antimatter counterpart of an electron, and a nearly massless particle called a neutrino. The neutrino interacts so weakly with matter that it usually escapes the sun almost immediately, passing through hundreds of thousands of kilometers of plasma as though the star were nearly empty. Most of the energy released in later steps remains trapped for a long journey outward, but the neutrino departs directly from the core. It carries a quiet message from the place where fusion is occurring at that moment. Detecting solar neutrinos on Earth therefore provides evidence that the sun is powered by nuclear reactions now, rather than merely releasing energy stored in some ancient event. The positron does not travel far. It soon meets an electron, and the two particles annihilate, converting their mass into energetic photons. Meanwhile, the newly formed deuterium nucleus remains in the crowded core. Unlike the first reaction, its next step happens comparatively quickly. It collides with another proton and combines with it, creating a light isotope of helium called helium-3. This nucleus contains two protons and one neutron. The reaction releases additional energy in the form of a photon. Across the core, the same sequence occurs again and again, though the first transformation remains the slow gate that controls the overall rate. Two separate helium-3 nuclei may eventually meet. When they fuse, they form a stable helium-4 nucleus containing two protons and two neutrons, while two excess protons are released back into the plasma. The complete chain has used four original hydrogen nuclei to create one helium nucleus. It has also released positrons, neutrinos, photons, and kinetic energy carried by particles. The products together have slightly less mass than the original ingredients. That missing mass has not vanished. It has become energy. This is the source of the sun's power. The loss is small for each completed chain, only a fraction of the starting mass, but the number of reactions is enormous. Every second, the solar core converts hundreds of millions of tons of hydrogen into helium. Several million tons of mass are transformed into energy during that same second. These figures sound like a pace that should empty the sun quickly, yet they represent only a minute share of the star's vast supply. The sun contains an amount of hydrogen so great that even a loss measured in millions of tons per second can continue for billions of years. The fusion process is not spread evenly through the whole star. It is concentrated in the core where temperature and density are highest. Most of the sun's hydrogen remains outside the active central region and does not currently participate in fusion. Even within the core, only a small portion is transformed during any short period. The rate is governed by the rarity of the first proton to neutron conversion. This weak interaction is so unlikely that an individual proton may remain in the core for billions of years before entering a successful chain. Once the first step occurs, the remaining steps proceed much faster. But the slow beginning controls the entire flow. The sun is therefore immensely powerful in total while being remarkably inefficient at the level of single particles. That inefficiency is one of the great protections of its lifetime. If the first reaction occurred easily, the core would consume hydrogen far more rapidly. Energy production would rise, the star would expand, and its life would be drastically shorter. Instead, the quantum barrier and the weakness of the transforming interaction impose restraint. The sun has enough particles to overcome rarity through sheer numbers, but not enough to turn that rarity into a sudden detonation. Fusion in the core is also different from an uncontrolled explosion because the reactions are embedded within hydrostatic equilibrium. Energy released by fusion heats the surrounding plasma and contributes to outward pressure. If the reaction rate increases, the core expands slightly. Expansion lowers its temperature and density. Making fusion less frequent, if the rate decreases, gravity compresses the core, raising temperature and density until reactions accelerate again. The proton-proton chain operates inside this self-correcting environment. It is not simply a source of energy, but part of a larger system that regulates its own conditions. The chain has several branches, and not every helium nucleus forms through exactly the same final route. In the Sun, the simplest branch dominates, but other pathways involve different intermediate nuclei and release neutrinos with different energies. These variations matter to scientists because the pattern of neutrinos reveals details about the core temperature and the relative importance of the reactions. For many years, detectors on Earth measured fewer solar neutrinos than theoretical models predicted. The difference once raised questions about whether the understanding of the Sun was incomplete. The solution came from particle physics. Neutrinos can change from one type into another while traveling, and early detectors were sensitive to only some types. When experiments accounted for this transformation, the missing particles were found in altered forms. The results strengthened both the model of solar fusion and the evidence that neutrinos possess a small amount of mass. A mystery inside the Sun helped reveal a deeper property of matter. The energy carried by photons has a different fate. A photon created in the core cannot travel straight to the surface. The plasma is far too dense. It is absorbed, scattered, and re-emitted repeatedly, sharing its energy with surrounding particles. The original high-energy radiation is gradually transformed into lower-energy light during a journey that may take many thousands of years. The energy eventually reaches regions where convection carries it outward more efficiently, and only near the photosphere does it finally escape into space. The sunlight reaching Earth has therefore lost any direct identity with a single fusion event, while neutrinos arrive almost unchanged from the core. Together, they reveal two timescales of the same star, the immediate nuclear activity at the center, and the delayed light emerging from its surface. The proton-proton chain explains how the Sun produces enough energy to illuminate an entire planetary system, but its deeper importance lies in its measured pace. 4 hydrogen nuclei become one helium nucleus through a sequence of rare transformations, brief encounters, and forces acting across distances smaller than an atom. The process is almost impossible for any particular set of particles, yet inevitable across a core containing more protons than ordinary language can meaningfully describe. Gravity creates the pressure, heat drives the collisions, quantum physics allows the barrier to be crossed, nuclear forces bind the new nuclei, and a small loss of mass becomes radiation and motion. Nothing in the chain resembles a flame, and nothing requires the fuel to burn quickly. The Sun endures because fusion is difficult. Its light is vast only because the core is vast, and its lifetime is long because the doorway to each reaction remains nearly closed. The Sun's power begins with a difference so small that it can be missed unless matter is measured with extraordinary care. When 4 hydrogen nuclei eventually become one helium nucleus, the finished helium nucleus does not weigh quite as much as the 4 original protons. The difference is less than 1% of the starting mass, yet it is not an error, and it is not lost material. It has been converted into energy. This is the meaning behind the relation between mass and energy expressed by Einstein's equation, in which a small amount of mass corresponds to a vast amount of energy because it is multiplied by the square of the speed of light. The equation reveals that mass is one form of stored energy, and that nuclear reactions can rearrange matter in ways that release part of it. In the Sun, this conversion happens continuously in the core, quietly enough to sustain stability and powerfully enough to illuminate the solar system. The reason the released energy is so large lies in the scale built into the equation. The speed of light is already an enormous value, and squaring it makes the conversion factor far greater. A tiny mass difference, therefore, becomes an immense quantity of energy. At the level of a single fusion chain, the release is still extremely small by everyday standards, yet the solar core completes an incomprehensible number of such chains every second. Across that enormous population of reactions, the small differences add together. Hundreds of millions of tons of hydrogen are transformed into slightly less helium each second, while several million tons of mass become energy. The total mass of the reaction products and emitted particles is lower than the total mass that entered the reactions. The difference appears as the motion of particles, energetic photons, and neutrinos. This mass loss is real, but compared with the total mass of the Sun, it is extraordinarily small. The star contains enough matter for the process to continue over billions of years without any noticeable change in its appearance from one human generation to the next. The source of the mass difference is the way atomic nuclei are bound together. A nucleus is not simply a collection of particles whose masses can be added without adjustment. Protons and neutrons are held by the strong nuclear force, and the bound nucleus has less total energy than the same particles would have if separated. Because mass and energy are linked, the lower energy bound state also has less mass. This missing amount is called the mass defect. Though nothing defective has occurred, it is a measure of the binding energy released when the nucleus forms. Helium-4 is especially tightly bound, which is why the transformation from hydrogen to helium produces so much energy. The new nucleus settles into a more stable arrangement, and the difference between the less tightly bound starting particles and the more tightly bound final nucleus is carried away. The Sun's light therefore comes from matter moving into a state of deeper nuclear stability. The energy does not emerge in one simple form. Some appears as the rapid motion of newly created nuclei and other particles. Collisions quickly distribute this motion through the surrounding plasma, increasing its thermal energy. Some appears as high-energy photons, which are absorbed almost immediately and re-emitted in new directions. A smaller portion is carried by neutrinos, which escape the Sun with little interaction. Most of the energy remains trapped in the interior at first, supporting pressure and beginning a slow outward migration. The core is therefore both the place where mass becomes energy and the place where that energy loses any simple connection to its original reaction. Within moments, the energy has been shared among countless particles. Over much longer periods, it moves outward through the changing conditions of the solar interior. The conversion rate is immense when measured against human technology. The Sun releases more energy each second than human civilization has used across its entire history. Yet the star is not straining to do so. Its luminosity is the natural result of its mass, composition, core temperature, and equilibrium. The fusion reactions are distributed through a large central volume rather than concentrated at a single point. Each tiny part of the core contributes a fraction of the total output, and the combined result becomes the steady luminosity observed at the surface. The Sun shines with remarkable consistency because the production of energy is spread through space and regulated through pressure. Even the conversion of millions of tons of mass each second represents only a slight draw on the Sun's reservoir. Over its entire main sequence life, only part of the hydrogen in the core will be fused, and only a small fraction of that fused mass becomes energy. This explains how the Sun can lose mass continuously without rapidly diminishing. The total mass converted during billions of years is significant, Yet the remaining sun is still overwhelmingly massive. It also loses matter through the solar wind and occasional eruptions, but fusion accounts for a distinct and steady reduction through mass-energy conversion. As the sun radiates, it becomes microscopically lighter. That loss slightly weakens its gravitational influence over immense spans of time, causing planetary orbits to expand by tiny amounts. The released energy also reveals why nuclear fusion is fundamentally different from chemical burning. In a chemical reaction, electrons rearrange among atoms, and the nuclei remain unchanged. The energy differences are relatively small because electromagnetic bonds between atoms are far weaker than nuclear binding. In fusion, the nuclei themselves are transformed. The energy scale is millions of times greater for the same amount of material. A chemical sun could not shine at its present rate for billions of years. It would exhaust any plausible fuel far too quickly. Gravitational contraction alone could also power the sun for only a limited period before the star became much smaller. The discovery that mass can become energy, combined with the understanding of nuclear reactions, resolves the old problem of solar age. It provides a source powerful enough to match the sun's luminosity and slow enough to match the geological and astronomical evidence for deep time. The energy created in the core does more than leave as sunlight. Before escaping, it helps maintain the very conditions that allow further fusion. It heats the plasma, contributes to pressure, and supports the layers above. In this sense, mass-energy conversion is woven into the structure of the star. If fusion stopped suddenly, the sun would continue shining for a time because energy is stored throughout its interior, but the core pressure would eventually decline. Gravity would compress the center, raising the temperature until new reactions became possible, or until a different stage of stellar evolution began. During the present phase, fusion replaces the energy radiated from the surface, allowing the sun to remain close to thermal balance. Energy is constantly leaving, but new energy is constantly being produced. The sun is neither cooling away nor heating without limit. It is passing energy from nuclear binding into radiation, particle motion, and eventually space. Only a tiny portion of the sun's total output reaches Earth. The planet intercepts a narrow fraction of the light spreading in all directions, yet that fraction drives weather, warms oceans and land, powers photosynthesis, and supports nearly every surface ecosystem. The rest continues outward, crossing the orbits of the other planets and fading into interstellar space. The sun does not aim its energy or ration it among worlds. It radiates because hot matter emits energy, and its spherical surface sends that energy outward in every direction. Earth happens to occupy one small part of that expanding sphere. The warmth of daylight is therefore the distant result of missing nuclear mass deep inside a star. Photons absorbed by soil, water, leaves, and atmosphere carry energy that begins in reactions hidden beneath hundreds of thousands of kilometers of plasma. The transformation from mass to light also proceeds without consuming matter in the ordinary sense. Most of the hydrogen's mass remains in the helium that is produced. Only the small binding difference becomes energy. This restraint is crucial. The sun does not convert whole protons directly into light. It reorganizes them into a more tightly bound nucleus and releases only the energy difference. Because the fraction is small, the fuel reservoir lasts. Because the conversion factor is immense, that small fraction is sufficient. The longevity and brightness of the sun are therefore not contradictory. The same physics allows both. A minute loss per reaction gives the star endurance, while the enormous number of reactions gives it power. Almost nothing changes in each individual event, yet across the core that almost nothing becomes almost everything the solar system receives as light and heat. The sun has shone for billions of years because nature has found a way to draw immense energy from a tiny change, repeating it steadily within a gravitationally regulated heart. The sun contains so much hydrogen that its fuel supply seems without limit. Yet abundance alone does not explain its endurance. A large store can still be spent quickly if the process using it is fast. The deeper reason the sun lasts for billions of years is that fusion is restricted, reluctant, and self-regulated. Most of the hydrogen in the star is not taking part in nuclear reactions. It remains in layers too cool and too diffuse for fusion to proceed at a meaningful rate. Even in the core, where temperature and pressure are highest, individual protons wait through immense spans of time before entering a successful reaction. The sun shines with tremendous total power because it contains an immense number of particles, not because those particles are consumed rapidly. This distinction separates a long-lived star from a brief release of energy. The active fusion region occupies only the central portion of the sun. Temperature falls with distance from the center, and the proton-proton chain is extremely sensitive to that temperature. A modest drop sharply reduces the likelihood that protons will approach closely enough for quantum tunneling and nuclear transformation. Beyond the core, hydrogen still fills the plasma, but the conditions no longer allow sustained energy production. The surrounding layers serve mainly as pathways for energy and as weight pressing down on the center. They do not burn like fuel in a flame spreading through wood. Fusion does not travel outward simply because hydrogen is present. Each region must independently reach the required temperature and density, and most of the sun never does during its stable main sequence life. This confinement preserves a vast reserve outside the active core, though much of that reserve will never be used in the same way because the sun does not mix all of its material efficiently into the center. In the deep interior, energy moves mainly through radiation, and the plasma remains stable against large-scale overturning. Matter there does not circulate freely from the surface to the center. Hydrogen in the outer regions cannot simply sink into the core to replace what has been consumed. As a result, the sun's usable fuel is smaller than its total hydrogen content, but it is still enormous enough to support roughly 10 billion years of main sequence shining. The present sun is a little less than halfway through that interval. Its age is about 4.5 billion years, and substantial hydrogen remains in the central region. The slowness of the first fusion step is even more important than the size of the reservoir. 2 protons must come close enough for the strong nuclear force to bind them, but electric repulsion keeps them apart. Quantum tunneling makes a close encounter possible, yet the resulting pair cannot remain as 2 protons. 1 proton must change into a neutron through the weak nuclear force. That transformation is extraordinarily rare. It acts like a narrow gate through which the entire proton-proton chain must pass. Once deuterium forms, later reactions occur much more quickly, but the first step controls the pace of the whole sequence. A typical proton can spend billions of years moving through the core before it participates in a successful fusion event. The core is not a place where every collision releases energy. Almost all collisions fail, while rare successes across an immense population add up to a steady luminosity. This inefficiency is not a flaw. It is the foundation of the sun's long life. If hydrogen fused easily at the temperatures found in the core, the reaction rate would rise enormously. The sun would produce far more energy, expand, and consume its central fuel much faster. Its stable lifetime would shrink, perhaps leaving too little time for complex planetary histories to unfold. Instead, the weak interaction slows the conversion of hydrogen into helium to a pace that gravity and pressure can regulate. The star releases energy quickly enough to balance the loss from its surface, but slowly enough to avoid exhausting the core. The quantity of fuel and the difficulty of using it fit together through the laws governing particles and stars. The amount of energy released from each completed fusion chain also contributes to endurance. Only a small fraction of the original hydrogen mass becomes energy. Most remains as helium. The Sun does not convert all of its fuel directly into radiation. It rearranges protons and neutrons into a more tightly bound state, releasing the difference in binding energy. That fraction is enough to power the star because mass carries an enormous energy equivalent, but it is small enough that the material reservoir declines gradually. Hundreds of millions of tons of hydrogen are processed each second, and several million tons of mass become energy. Yet the Sun is so massive that this continuous conversion barely changes its total weight over short timescales. Human intuition is poorly suited to such contrast. The amount consumed each second sounds overwhelming, but the supply is greater by an almost incomprehensible margin. A star can spend millions of tons every second and still behave like a careful saver when its account is measured in stellar mass. The Sun also regulates how quickly it spends that fuel. Fusion depends strongly on core temperature. If the reaction rate rises, extra energy increases pressure and causes the core to expand slightly. Expansion cools the plasma and reduces its density, making fusion less frequent. If the reaction rate falls, gravity compresses the core, which raises temperature and density and restores the reactions. This negative feedback prevents small changes from becoming runaway events. The Sun cannot suddenly burn much faster without changing the conditions that allow the increase. Greater energy output produces expansion, and expansion suppresses the output. Lower output produces contraction, and contraction strengthens it. The same star that holds the fuel also controls the rate at which the fuel can be used. This regulation works because the solar core is made of hot plasma. When heated, it tends to expand. When cooled, it tends to contract. Later in the lives of some stars, matter can enter unusual states in which pressure no longer responds to temperature in the same stabilizing way. Under those conditions, nuclear reactions may become explosive. The present solar core is not in such a state. Its pressure remains closely connected to heat and density, allowing expansion to serve as a brake. The fuel burns slowly because the nuclear gate is narrow, the active region is limited, and the core can expand when energy production rises. As helium accumulates, however, the balance changes gradually. 4 hydrogen nuclei become 1 helium nucleus. Reducing the number of free particles available to provide pressure, the core slowly contracts under gravity, and contraction raises the temperature. A hotter core increases the fusion rate, so the Sun becomes more luminous over time even while its hydrogen supply decreases. This seems opposite to the behavior of a dying fire, but a star is governed by gravity. As usable fuel declines, the core does not simply cool, it compresses and heats, allowing the remaining hydrogen to react more rapidly. The Sun today shines more brightly than it did when Earth was young, and the increase continues slowly. Its fuel lasts for billions of years, but the rate of use is not perfectly constant. The star moves through a sequence of balanced states, each a little hotter and brighter than the last. Even so, the changes are gradual because the core's structure responds over immense timescales. The Sun does not race toward its final hydrogen reaction. It evolves almost imperceptibly from one stable condition to another. Only after the central hydrogen becomes too depleted will the core contract enough to force a major reorganization. Hydrogen fusion will continue in a shell around an increasingly helium-rich center, and the outer layers will expand. That distant transformation marks the end of the Sun's main sequence restraint. But it does not mean all hydrogen in the star has been consumed. Large amounts will remain outside the core. The end comes because the central region, where pressure and temperature are sufficient, can no longer sustain the same pattern of reactions. The usable fuel is defined by location and conditions, not simply by total abundance. The answer to why the sun's fuel lasts is therefore layered. The star begins with an immense supply of hydrogen, but only a fraction lies within the active core. The first step of fusion is exceptionally rare. Each reaction converts only a small share of mass into energy. The hot plasma expands when production rises, cooling the core and slowing the process. Gravity then maintains the balance over billions of years. The sun endures because its power emerges from restraint. The core burns with enough intensity to support a star, yet each proton meets a long delay. Each reaction releases a measured fraction, and each increase carries the cause of its own correction. Beneath the overwhelming brightness lies a process that advances almost patiently, one reluctant collision at a time. The sun remains stable because every change in its core creates a response that pushes the star back toward balance. Fusion is extremely sensitive to temperature. A small rise in the core temperature allows protons to move faster, collide more often, and reach the conditions needed for nuclear reactions with greater frequency. Left alone, that sensitivity might seem dangerous. More fusion would produce more heat, and more heat could produce still more fusion. Yet the solar core does not allow this chain to grow without limit. The extra energy increases pressure, and the increased pressure causes the core to expand. As the plasma expands, it cools and becomes less dense. The fusion rate then slows. A process that begins with greater energy production ends by reducing the conditions that caused it. The same pattern works in reverse. If fusion weakens, the core loses support. Gravity compresses it, and compression raises the temperature and density. The reaction rate increases again. This natural feedback acts as the sun's thermostat, not through any separate control system, but through the ordinary behavior of hot matter under gravity. The stabilizing cycle begins with the relationship between pressure and temperature. In the solar core, most pressure comes from the rapid motion of particles. Hotter particles move more energetically and collide more forcefully, creating greater outward pressure. When fusion releases additional energy, the surrounding plasma warms, the pressure rises, and the core pushes outward against the weight above it. Expansion requires work because the plasma must lift overlying layers against gravity. Part of the extra energy is therefore used to enlarge the core rather than simply raising its temperature. As the same amount of matter occupies a greater volume, the density falls, the particles spread farther apart, collisions become less frequent, and fusion slows. Expansion also cools the gas because energy is spent in doing work, and because the particle motions are distributed through a larger region. The core returns toward its earlier state before a runaway can develop. When energy production falls, the opposite sequence unfolds. Pressure decreases slightly, and gravity gains a small advantage. The core contracts under the weight of the star. Falling inward converts gravitational energy into heat. Particles become more crowded and move more rapidly. The higher density increases the number of collisions, while the higher temperature raises the chance that protons can cross the electrical barrier separating them. Fusion strengthens, pressure is restored, and contraction slows. Gravity therefore serves as both threat and correction. It can compress the star, but that compression creates the heat needed to rebuild support. The sun remains poised between expansion and collapse because each tendency awakens the force that opposes it. This behavior is called negative feedback. A change does not reinforce itself indefinitely. It produces consequences that reduce the original change. Negative feedback appears throughout stable natural systems, but inside a star it operates on an immense scale. The entire core participates, adjusting its size, density, and temperature in response to slight shifts in energy production. These adjustments are not sudden. The sun is too large for every region to respond at once, and pressure waves and gradual structural changes carry the response. Yet the physical direction remains consistent. Excess heating leads toward expansion and cooling, while insufficient heating leads toward contraction and warming. Over millions and billions of years, this feedback keeps the star within the narrow range that allows steady hydrogen fusion. The thermostat works because the core is an ordinary hot plasma rather than a rigid substance. Its pressure responds strongly to temperature. When heated, it expands. When cooled, it contracts. This simple property gives the sun a reliable brake. In some other stellar environments, matter can become so densely packed that pressure no longer depends mainly on temperature. Under those conditions, heating may fail to cause expansion, and nuclear reactions can accelerate without immediate cooling. Explosive events can then occur. The present sun does not face that danger in its hydrogen-burning core. Its plasma remains able to expand, making temperature increases self-limiting. The star's calmness is therefore tied to the particular state of matter at its center. The sun also regulates itself through the relationship between energy production and energy loss. Energy generated in the core must eventually pass through the surrounding layers and escape from the surface. If the core produces slightly more energy than the outer layers carry away, the interior stores some of the excess, pressure rises, and the star expands. If it produces less than the surface loses, pressure weakens and contraction adds gravitational heat. The sun continually adjusts so that production and loss remain close over long time scales. This regulation explains why the sun does not flicker wildly as nuclear reactions occur. Fusion events are discrete and microscopic, but their number is so enormous that the total output appears smooth. Local fluctuations average together across the core. A temporary rise in reactions within one small region is absorbed into the surrounding plasma and moderated by expansion, heat flow, and pressure. The surface can vary because of magnetic activity, but deep below, the nuclear engine remains remarkably steady. The apparent disorder above rests upon a core whose feedback mechanisms preserve a measured output. The thermostat also guides the sun through gradual evolution. As hydrogen becomes helium, the core's composition changes. 4 hydrogen nuclei ultimately become one helium nucleus. So the number of free particles decreases. With fewer particles contributing to pressure, the core cannot support the same weight at exactly the same temperature and density. Gravity causes a slow contraction. That contraction raises the temperature, and the hotter core increases the fusion rate. The sun therefore becomes gradually brighter as it ages. This is not a failure of regulation. It is the thermostat finding a new balance as the fuel and composition change. The star moves through a sequence of stable states rather than remaining perfectly unchanged. Each state is slightly hotter and more luminous than the one before, yet the movement between them is so slow that the sun stays calm across geological ages. Early in its main sequence life, the sun shines more faintly than it does now. Over time, its core grows richer in helium, contracts, and heats. The increasing temperature allows the remaining hydrogen to fuse more rapidly. The outward pressure rises enough to maintain equilibrium, while the outer layers adjust. The thermostat does not hold the luminosity at one fixed value. It prevents sudden departures while allowing the long-term changes required by stellar evolution. Stability and change therefore coexist. The sun is stable because it changes in a controlled way, and it changes because the balance must respond to the gradual transformation of its core. This distinction helps explain why a star can endure for billions of years without being static. The same feedback prevents an abrupt shutdown. If the core produces less energy, gravity does not simply allow the sun to cool into darkness. Contraction releases energy and raises the temperature until fusion recovers. Gravitational contraction alone cannot sustain the Sun for the age revealed by geology. But within the modern Sun, it remains an essential supporting process. It does not provide most of the present luminosity, yet it restores the conditions needed for nuclear energy whenever pressure weakens. Gravity remains an active partner in the regulation of fusion. The balance also prevents the core from reacting like a terrestrial fire. A fire can spread when heat ignites nearby fuel, and more burning creates more heat. The solar core behaves differently. Heating changes the structure of the fuel itself. The plasma expands, density falls, and nuclear encounters become less likely. The star's enormous size makes the response slow, but its direction is stabilizing. Greater fusion builds its own brake, and weaker fusion builds its own correction. This is why the Sun can release a vast flow of energy without behaving like an explosion. Its power is held inside a system that continuously converts excess into expansion and deficiency into compression. The natural thermostat is therefore one of the deepest answers to the Sun's longevity. Hydrogen is abundant, fusion is slow, and only the core is active. But these advantages would be less secure without feedback. The Sun lasts because it does not merely burn fuel. It responds to the way that fuel burns. Every slight increase in heat opens the star outward, and every slight decrease allows gravity to draw it inward. Between those motions, temperature and pressure remain within the range required for steady fusion. Instability creates the means of stability, and the star continues shining by correcting itself almost as soon as it begins to drift. The energy created in the Sun's core does not immediately become the sunlight that reaches Earth. It begins deep inside a sphere of plasma so dense that light cannot travel through it in a straight line. A photon produced by fusion may move only a tiny distance before meeting an electron or atomic nucleus. It is absorbed, scattered, or re-emitted in another direction, and the process repeats again and again. The photon does not preserve a simple path from the center to the surface. Its journey is a random walk, a slow and tangled migration through matter that is constantly colliding, shifting, and exchanging energy. The distance from the core to the visible surface is less than the distance light can cross in a few seconds through empty space. Yet inside the Sun, the same energy may take tens of thousands or even hundreds of thousands of years to emerge. The difference comes from density. Empty space offers almost nothing to interrupt a photon. But the solar interior is crowded beyond ordinary experience. Every step outward is broken by another encounter, and every encounter changes the direction, energy, or identity of the radiation moving through the star. Near the core, fusion first produces high-energy photons, often in the form of gamma radiation. These photons carry far more energy than visible light, but they do not remain unchanged. They collide with charged particles and transfer part of their energy. New photons are produced at lower energies, and repeated interactions spread the original energy among many particles. The energy becomes less concentrated and more widely distributed. By the time it approaches the surface, it no longer resembles the radiation created in the nuclear reaction. The original photon may have vanished almost immediately, replaced by a long chain of absorptions and emissions. What survives is not a particular particle of light, but a quantity of energy moving gradually outward. This distinction explains why sunlight is ancient without requiring any single photon to spend the entire journey intact. The energy begins in the core, changes form countless times, and only much later leaves the photosphere as visible and infrared radiation. The inner region through which most of this slow migration occurs is called the radiative zone. It surrounds the core and extends through a large part of the Sun's radius. In this region, energy moves mainly by radiation, rather than by large-scale rising and sinking of plasma. The temperature is still immense, but it decreases outward. Photons repeatedly move from hotter regions toward cooler ones, though individual steps can point in any direction. The overall flow is outward because the center contains more energy, and the surface continually loses energy to space. The process resembles diffusion. A drop of dye placed in water spreads because countless random motions create a gradual movement from concentration toward dilution. In the sun, radiation diffuses from the hot center toward the cooler exterior. The direction of each interaction is uncertain, but the combined effect of uncountable encounters carries energy outward over long timescales. The radiative zone remains relatively stable against convection, because temperature and density change in a way that does not strongly encourage large parcels of plasma to rise. Material still moves, but it does not overturn on the enormous scale found farther out. The energy therefore continues through repeated photon interactions. As it travels, the pressure, temperature, and density slowly decline. Different kinds of particles absorb and scatter radiation in different ways, so the opacity of the plasma changes with depth. Opacity describes how difficult it is for radiation to pass through matter. High opacity traps energy effectively, while lower opacity allows it to move more freely. The sun's internal structure depends partly on how opacity changes as elements lose or regain electrons under varying conditions. Even small amounts of heavier elements influence the flow, because their many possible electron arrangements interact strongly with radiation. The sun is mostly hydrogen and helium, yet the thin mixture of other elements helps shape the path that energy takes. Eventually, the outward moving energy reaches a region where radiation becomes less efficient at carrying the required flow. The plasma is cooler than it is near the core, and its interaction with light changes. Energy begins to accumulate beneath the outer layers, steepening the difference in temperature with depth. Hotter material below becomes buoyant because it is less dense than the cooler material above. Large parcels of plasma start to rise. This marks the convective zone, where energy is transported mainly by the physical movement of matter. Convection is familiar in a heated liquid. Where warm material rises, cools near the top, and sinks again. Inside the sun, the same general pattern occurs on a colossal scale. Rising columns carry heat toward the surface, while cooler plasma descends to replace them. The motion is turbulent, complex, and influenced by rotation and magnetic fields, but its basic purpose in the energy flow is simple. When radiation can no longer move heat efficiently enough, matter itself begins to move. A rising parcel of plasma expands as the surrounding pressure falls. Expansion cools it, even while it continues carrying energy upward. Near the surface, the plasma releases radiation more easily. After losing heat, it becomes denser and sinks back into the interior. This cycle produces a restless pattern beneath the visible face of the sun. At the photosphere, the tops of convective cells appear as granulation, a texture of bright centers and darker edges spread across the surface. The bright areas mark hotter plasma rising from below. The darker boundaries show cooler material descending. Each cell is temporary, changing over minutes as new material rises and old patterns dissolve. The photosphere looks smooth from Earth because of distance, but close observation reveals a surface in continual motion. The apparent stillness of sunlight is created by averaging together countless changing cells. The photosphere is not a solid surface. It is the layer where the plasma becomes transparent enough for photons to escape without immediately being absorbed again. Beneath it, the mean distance between interactions is short. Above it, light can travel freely into space. The transition occurs across a relatively thin region compared with the sun's enormous size, so it appears to define a sharp edge. yet there is no ground, crust, or boundary that could be touched. There is only a gradual thinning of gas until radiation breaks free. Once a photon leaves the photosphere in an outward direction, its long delay is over. It crosses the distance to Earth in a little more than 8 minutes. The contrast is striking. Energy may spend an age working through the solar interior, then complete the final journey across interplanetary space in minutes. The sunlight arriving now carries energy that may have begun its outward migration before the earliest known modern humans appeared. The nuclear reactions producing energy at this moment will not contribute directly to the visible surface for a very long time, though the sun's structure responds to changes through pressure and waves on much shorter timescales. The surface glow is therefore a release from a deep reservoir, continuously renewed, but never instantly connected to the core. This long delay helps smooth the sun's output. The energy generated by fusion is mixed, scattered, stored, and redistributed before escaping. Sudden microscopic variations in the core cannot appear immediately as flashes at the surface. The enormous radiative and convective layers act as a buffer, blending the output across time and space. Solar brightness does vary slightly because of magnetic activity, sunspots, and bright regions, but the nuclear source remains hidden beneath an envelope that prevents abrupt changes from reaching the exterior. The journey outward is not merely a delay, it is part of the mechanism that makes the sun steady. Trapped radiation supports the star. Convection carries heat without tearing the structure apart, and the photosphere releases energy at a rate the interior can replace. From the first fusion reaction to the final escape of visible light, every stage belongs to the same balance. The core makes energy slowly. The radiative zone diffuses it patiently. The convective zone lifts it through rising plasma. The photosphere opens into space. Ancient energy finally crosses the darkness, reaches planets, warms surfaces, and becomes part of weather, chemistry, and life. The sunlight that seems immediate is the final step of a journey hidden for ages inside the star. Ancient light searches for escape, and when it finally succeeds, the universe receives only the calm surface of a passage almost unimaginably long. The sun's visible surface seems smooth from a distance, but close observation reveals a restless world of rising plasma, darkened regions, bright rims, twisting magnetic loops, and sudden eruptions. Beneath this activity, the star's core continues its measured work, producing energy through fusion at a remarkably steady rate. The contrast is striking. Deep inside, the sun is regulated by gravity, pressure, and slow nuclear reactions. Near the surface, the same star appears turbulent and changeable. This disorder does not mean the fusion engine is unstable. It arises from the movement of charged plasma through the outer layers and from the magnetic fields created by that motion. The photosphere, the layer from which most visible sunlight escapes, is therefore not a calm boundary. It is the bright face of a star whose outer regions are constantly shifting. The sun is not made of ordinary gas in the familiar sense. Its temperatures are high enough to strip electrons from many atoms, creating plasma, a fluid of positively charged nuclei and negatively charged electrons. Charged particles respond to magnetic fields, and when they move, they can also generate magnetic fields. The sun rotates, but not as a solid body. Regions near the equator complete a rotation more quickly than regions closer to the poles. At the same time, convection carries hot plasma upward and cooler plasma downward through the outer layers. Rotation, convection, and electrical currents combine to produce a vast magnetic dynamo. The details remain complex, but the broad result is clear. The sun continually creates, stretches, twists, and rearranges magnetic fields throughout its interior and atmosphere. These fields can emerge through the photosphere in looping structures, linking one region of the surface to another. Where magnetic fields become especially concentrated, they interfere with the normal flow of heat from below. Convection is partly suppressed. So less energy reaches the surface in that area. The plasma remains extremely hot, but it is cooler than the surrounding photosphere and therefore appears dark by comparison. This is a sunspot. A sunspot is not a hole, and it is not truly black. If isolated from the brighter surface around it, it would shine intensely. It seems dark only because the neighbouring photosphere is hotter and more luminous. Sunspots often form in groups, with magnetic field lines connecting regions of opposite polarity. Some are larger than Earth, and the most complex groups can spread across enormous areas. Their number rises and falls in a pattern lasting roughly 11 years, known as the solar activity cycle. Near the low point, the surface may remain almost free of spots. Near the high point, many active regions can appear and eruptions become more frequent. The cycle reflects a broader reversal of the Sun's global magnetic field over a complete magnetic cycle. The field changes direction and eventually returns to its earlier orientation. The visible spots are therefore traces of a deeper process taking place through the moving plasma. Around sunspots, bright regions called faculae can form where concentrated magnetic fields alter the surface and allow hot material to be seen more clearly. These bright areas can outweigh the dimming caused by the spots themselves. As a result, the Sun may become slightly brighter overall during periods of strong magnetic activity. Even though more dark spots are present, the change is small compared with the Sun's total output, but it reveals that surface brightness depends on a balance between dark and bright magnetic features. The nuclear energy produced in the core remains steady on these timescales. The small variation observed from outside comes mainly from the changing pattern of the outer layers. Magnetism also guides plasma above the photosphere. Charged particles tend to move along magnetic field lines, tracing vast arches through the solar atmosphere. These structures can appear as prominences when seen against the darkness of space, or as dark filaments when viewed against the bright solar disk. Some remain stable for days or weeks, suspended by magnetic forces above the surface. Others twist, rise, and collapse. Their scale can dwarf planets, yet they form within an atmosphere that is extremely thin compared with the layers below. The magnetic field gives this tenuous plasma structure, holding it in long curves that would otherwise disperse or fall. Above the photosphere lies the chromosphere and farther out, the corona. The corona is far less dense than the visible surface, yet its temperature reaches more than 1,000,000 degrees Celsius, far hotter than the photosphere beneath it. This is one of the Sun's enduring mysteries. Heat normally flows from hotter regions toward cooler ones, so an atmosphere becoming hotter with height demands an additional energy source. Magnetic waves and countless small releases of magnetic energy appear to play major roles. Motions below the surface shake and twist field lines, sending energy upward. Magnetic fields can also break and reconnect in new arrangements, converting stored magnetic energy into heat and particle motion. The exact contributions of these processes remain under study, but the corona's extreme temperature is closely tied to the restless magnetism rising from the Sun. Magnetic reconnection can also produce sudden and powerful events. Field lines in an active region may become twisted and stressed as plasma moves beneath them. Energy accumulates in the magnetic configuration, much like energy stored in a tightly bent spring. When the field rearranges, part of that energy can be released rapidly as a solar flare. A flare produces intense radiation across a wide range of wavelengths, including ultraviolet light and X-rays. It can accelerate charged particles to high speeds and disturb the solar atmosphere within minutes. Even a powerful flare does not come from a sudden increase in core fusion. It is an atmospheric event driven by magnetic energy that has been stored and released near the surface. The distinction preserves the larger picture of solar stability. The core remains calm while the magnetic exterior produces brief outbursts. A related but distinct event is a coronal mass ejection, in which an immense cloud of magnetized plasma is thrown into space. A flare is mainly a burst of radiation and energetic particles, while a coronal mass ejection carries a large amount of solar material outward. The two can occur together, but not every flare produces a major ejection, and not every ejection is accompanied by the strongest kind of flare. When an ejected cloud is directed toward Earth, it may reach the planet after travelling through interplanetary space for several days. Earth's magnetic field deflects much of the incoming material, but some energy can enter the upper atmosphere and magnetosphere. Charged particles are guided toward polar regions, where they excite atoms and molecules in the air. As those particles release energy, the atmosphere glows in moving curtains and arcs called auroras. The same interaction can disturb satellites, radio communication, navigation systems, and electrical networks. Solar storms therefore connect the turbulence of the photosphere and corona with the technology and atmosphere of a distant planet. The Sun also releases a continuous solar wind, a stream of charged particles flowing outward from the corona. The solar wind fills the planetary system and carries the Sun's magnetic influence far beyond the visible disk. Its speed and density vary, especially when active regions and coronal holes alter the flow. Earth moves within this changing environment while its magnetic field forms a protective cavity around the planet. The solar wind is another reminder that the Sun does not end at the photosphere. Its outer atmosphere extends into space, becoming thinner but still shaping the region through which planets travel. Yet beneath sunspots, flares, prominences, and the solar wind, the central explanation for the Sun's age remains unchanged. Magnetic activity rearranges energy already moving through the outer layers. It does not consume the hydrogen reservoir at a dramatically different pace. The core continues to fuse hydrogen slowly, and the surrounding interior continues to transport that energy outward. Surface storms may alter the light reaching space by a small amount, but they do not threaten the long balance between gravity and pressure. The Sun can therefore wear a chaotic face while keeping a stable heart. Its visible surface is a meeting place between ancient energy rising from below and magnetic structures changing from hour to hour. Bright cells appear and vanish, spots grow, divide, and fade. Loops rise into the corona, fields reconnect, radiation flashes, and clouds of plasma escape into the solar system. All of this unfolds above a core whose fuel is being used with extraordinary restraint. The turbulence is real, but it belongs to the outer expression of a star that remains deeply regulated. Calm power wears a chaotic face, and the light that has endured for billions of years emerges through a surface that never truly rests. The Sun carries no visible inscription of its age. Its surface changes from minute to minute. Its magnetic patterns rise and fade, and the light leaving the photosphere reveals conditions near the present moment, rather than a record of its beginning. Yet the estimate that the Sun is about 4.5 billion years old is not a guess built from appearance. It emerges from several independent lines of evidence that meet at the same span of deep time. The most direct clocks are not found inside the Sun itself, because the solar interior is too hot for the original solid material of its birth to survive. Instead, the age is preserved in ancient rocks that formed from the same cloud. Meteorites contain minerals that solidified near the beginning of the solar system, and their atoms have been changing at known rates ever since. radioactive elements decay into other elements through processes governed by nuclear physics. Each isotope has a characteristic half-life, the time required for half of a given quantity to transform. By measuring the remaining parent atoms and the daughter products created by decay, scientists can calculate how long a mineral has existed as a closed system. The method does not depend on a single isotope or one unusual stone. Different radioactive pairs can be measured in many meteorites, and the oldest results gather around an age of roughly 4,560,000,000 years. This is the age of the first solid materials known to have formed in the solar system, not necessarily the exact instant when the central protostar begins to collapse. The difference is small on the scale of billions of years. The Sun forms during the same broad interval, growing at the center while dust and rock condense in the surrounding disk. The meteorites therefore act as surviving fragments of the Sun's birth environment. Their radioactive clocks begin when their minerals cool enough to lock atoms into stable crystal structures. Once enclosed, the parent and daughter isotopes remain trapped unless later heating or alteration disturbs them. The most useful samples preserve regions that have changed little since formation. Some meteorites contain tiny inclusions rich in calcium and aluminum, among the earliest known solids to condense from the hot young solar nebula. These inclusions provide some of the oldest dates in planetary science. Other components form slightly later, allowing the first few million years of solar system history to be arranged in sequence. The evidence reveals not only great age but a period of rapid construction. Dust becomes rock, small bodies grow, collisions occur, and planets begin assembling while the young sun is still settling into its stable state. Earth cannot preserve such a simple record because its crust is active. Plate tectonics, melting, erosion, impacts, and chemical alteration repeatedly destroy or transform ancient rocks. The oldest surviving terrestrial minerals are younger than the first meteorite solids and represent fragments rather than a complete planetary surface. The Moon retains older terrain, but even lunar rocks form after the solar system has already begun. Primitive meteorites are therefore more direct witnesses to the beginning. They are not pieces of the Sun, yet they share its origin. Their elements come from the same mixture of interstellar gas and dust, and their ages mark the time when that mixture becomes the organized solar system. Radioactive dating gains strength through agreement. Uranium can decay into lead through more than one chain, and each chain has a different half-life. Rubidium decays into strontium, samarium decays into neodymium. Other isotope systems provide additional clocks suited to different materials and timescales. When several methods applied to the same sample produce compatible results, the chance of a shared error becomes smaller. Scientists also use internal comparison methods that do not require assuming how much daughter material existed at the beginning. Minerals from the same object can be measured against one another, and their isotope ratios form patterns whose slopes reveal age. The calculation rests on measured nuclear decay rates and the chemistry of the sample rather than on an imagined initial condition. Disturbance can reset or partially alter a clock, but this usually leaves recognizable inconsistencies. A reheated meteorite may record both its original formation and a later collision, preserving a more complex history rather than simply giving a false age. The Sun's age is also tested through stellar physics. A star's mass, composition, brightness, radius, and internal structure determine how quickly it evolves. The Sun's mass is measured through the motions of planets, while its radius and luminosity are observed directly. Its surface composition is studied through spectroscopy, in which dark and bright lines in sunlight reveal the elements absorbing and emitting specific wavelengths. These measurements become inputs for models that calculate how a star changes as hydrogen is fused into helium. A model begins with a young sun and follows the gradual adjustment of pressure, temperature, density, chemical composition, and energy output. After about 4.5 billion years, a successful model must reproduce the Sun that exists now. It must match the observed luminosity and radius, and it must also agree with less obvious evidence from the hidden interior. Heliosismology provides one of the strongest tests. Waves travel through the Sun and cause its surface to oscillate in patterns that can be measured. Their speeds and paths depend on temperature, density, and composition at different depths. By studying these oscillations, scientists infer the internal sound speed profile and the depth of the convective zone. Solar models of the correct age and composition closely reproduce many of these features. A model that is much younger would have a different core composition and structure. A much older main sequence Sun would have converted more hydrogen into helium and would be brighter, hotter at the centre, and closer to leaving its stable phase. The oscillations therefore act as a present-day record of slow internal evolution. Neutrinos offer another test. The kinds and energies of neutrinos escaping from the core depend on the fusion reactions occurring there and on the core temperature. Detectors on Earth measure these particles, confirming that the central conditions broadly match the predictions of solar models. The neutrinos do not directly announce an age, but they verify the engine whose gradual changes are used to calculate it. When meteorite clocks and stellar models point toward the same history, they support one another through entirely different physics. One line of evidence depends on radioactive decay and solid minerals, the other depends on gravity, plasma, nuclear fusion, and the structure of a star. Their agreement is powerful because the methods do not share the same assumptions or materials. Comparisons with other stars add a wider context. The galaxy contains stars with many masses and ages, some newly formed in clouds, some stable like the Sun, and some entering their final stages. Star clusters are especially useful because their members form at roughly the same time but possess different masses. The most massive stars use fuel rapidly and leave the main sequence first, while lower mass stars remain stable longer. The pattern of stars still shining normally, and those already evolving away from that state reveals the age of the cluster. When the Sun is placed among these broader stellar populations, its properties fit those of a mature but not elderly main sequence star. It is older than the bright young stars of recent clusters, and younger than many ancient stars formed early in the history of the Milky Way. Its chemical composition also carries traces of its place in galactic history. The Sun contains elements heavier than helium that must have been created in earlier generations of stars and scattered into space before the solar system formed. It is therefore not among the galaxy's first stars. Its birth requires a universe already old enough for previous stars to live, manufacture heavier elements, and return material to interstellar clouds. The solar age sits naturally within this larger chronology. No single measurement contains the entire answer. Meteorites mark the formation of solids. Radioactive decay measures elapsed time. Stellar models follow the slow transformation of the core. Heliosismology tests the internal structure. Neutrinos confirm present fusion conditions. Other stars reveal how objects of different masses change across time. Together, these methods turn an invisible past into a physical history. The figure of about 4.5 billion years remains an estimate with carefully measured uncertainty, but its foundation is broad and consistent. Deep time leaves no clock face on the Sun, yet it leaves patterns in lead atoms, vibrations in plasma, the changing mixture of hydrogen and helium, and the orderly lives of stars across the galaxy. The Sun's age is known because matter remembers change, and several forms of that memory converge on the same ancient beginning. The Sun has shone for about 4.5 billion years, but its endurance is not permanence. Every second, hydrogen disappears from the core and helium takes its place. The change is slow enough to be invisible across a human lifetime, yet it steadily alters the star from within. The sun remains stable because gravity, pressure, and fusion continually adjust to one another, but the balance cannot remain identical forever. The core is not being refilled with fresh hydrogen from the outer layers, and the reactions that sustain the main sequence gradually reduce the supply available in the hottest central region. The star still has billions of years ahead, but its future is already contained in the quiet transformation now taking place. As helium accumulates, the core becomes denser. 4 hydrogen nuclei have become 1 helium nucleus, so fewer free particles remain to share the pressure. Gravity responds by compressing the central region. Compression raises the temperature, and the hotter core causes the remaining hydrogen to fuse more rapidly. The sun therefore grows brighter as it ages. This may seem opposite to the behavior of an ordinary fire, which weakens as fuel is consumed. But a star is controlled by gravity. Less usable hydrogen does not simply mean less heat. It means the core must contract to support the same weight, and contraction makes the remaining fuel react faster. The young sun is significantly fainter than the present sun, while the future sun will be brighter still. The increase is gradual, unfolding across hundreds of millions of years, but planetary climates can respond long before the star reaches the end of its main sequence life. Earth already exists near the inner region where liquid water can remain stable under present conditions. As solar luminosity rises, more energy reaches the planet. Warmer oceans release more water vapor, and water vapor strengthens atmospheric warming over very long timescales. This feedback may make the surface increasingly hostile to complex life. Carbon dioxide may be drawn down through weathering, weakening photosynthesis, while the oceans slowly lose water to the upper atmosphere and space. These changes belong to the distant future and depend on many details of planetary climate, but they reveal an important truth. The sun does not need to become a red giant before Earth feels its aging. The slow brightening of a stable star can transform a planet while the star itself still appears calm. Eventually, the concentration of hydrogen at the very center becomes too low to sustain the same pattern of fusion. This does not mean all hydrogen in the sun has vanished. Large amounts remain in the surrounding layers, but the central region where temperature and density are highest has become dominated by helium. Without sufficient hydrogen fusion in the core, energy production there declines. Gravity then compresses the inert helium center. The contraction releases gravitational energy and raises the temperature around it. A shell of hydrogen just outside the core becomes hot enough to fuse more intensely than before. Energy production moves outward into this shell, surrounding a contracting helium center. This new arrangement changes the whole star. The hydrogen-burning shell adds helium to the core, making it more massive and more compressed. Its increased energy pushes strongly on the outer layers, and the sun expands. As the surface spreads over a much larger area, it cools even while the total luminosity rises. The star becomes a red giant, not because its surface is cold, but because it is cooler than the present photosphere and radiates more strongly at redder wavelengths. Its outer atmosphere grows vast and tenuous, reaching far beyond the present solar radius. The inner planets face destruction or severe transformation. Mercury and Venus are expected to be engulfed. Earth's fate is less certain because the expanding sun loses mass, weakening its gravitational pull and allowing planetary orbits to move outward. At the same time, tides and interaction with the enlarged solar atmosphere may draw Earth inward. Even if the planet avoids direct engulfment, its surface will already have been sterilized and melted long before the red giant reaches its greatest size. The familiar solar system becomes a place of swollen light, altered orbits, and evaporated worlds. Yet the red giant phase is not the final moment. The helium core continues to contract because helium fusion requires much higher temperatures than hydrogen fusion. The surrounding hydrogen shell keeps adding mass and pressure until the core reaches roughly 100 million degrees Celsius. At that threshold, helium nuclei can begin to combine. 3 helium nuclei eventually form carbon, and some reactions produce oxygen in a star of the Sun's mass. The onset occurs rapidly in an event called the helium flash. The term suggests a visible explosion, but the event remains hidden within the deep interior. The core has entered a dense state in which pressure is not initially controlled by temperature in the usual way. So the first rise in helium fusion cannot immediately cause expansion and cooling. The reaction rate increases sharply until the core becomes hot enough to expand and return to a more ordinary condition. The enormous release of energy is absorbed within the star rather than blasting the outer layers away. Afterward, the Sun settles into another period of relative stability, now fusing helium in the core and hydrogen in a surrounding shell. This phase lasts far less time than the hydrogen-burning main sequence because the available helium fuel is smaller and the reactions proceed more rapidly. The star has entered old age. As helium becomes carbon and oxygen, the central fuel again declines. The Sun is not massive enough to heat its core sufficiently for carbon fusion. When helium fusion ends, a carbon and oxygen core remains, surrounded by shells where helium and hydrogen continue reacting for a time. The outer layers become unstable. Pulsations and strong stellar winds lift gas away from the star. Over thousands of years, the Sun sheds much of its envelope into space. Ultraviolet radiation from the exposed hot core illuminates the escaping gas, producing a planetary nebula, a glowing structure whose name has nothing to do with planets. The form may be spherical, elliptical, or shaped into more complex lobes by rotation, magnetic fields, or companions. It is a brief and delicate final display, returning hydrogen, helium, carbon, oxygen, and other material to interstellar space. Some of that matter may later join new clouds, new stars, and new planetary systems. The Sun begins from recycled stellar material and ends by contributing material to another generation. At the center of the fading nebula, the former solar core becomes a white dwarf. It is no longer producing energy through sustained fusion. Gravity compresses it to a size comparable to Earth, while it retains a substantial fraction of the Sun's mass. The matter is supported by electron degeneracy pressure, a quantum effect arising because electrons cannot all occupy the same states. This pressure prevents further collapse even though the star has lost the thermal support of fusion. The white dwarf begins extremely hot, shining from stored heat left by its former life. It cools gradually across spans far longer than the present age of the universe. No sudden darkness arrives. The remnant fades almost beyond imagination, moving toward a cold state that no white dwarf has yet had enough cosmic time to reach. The Sun's final future therefore reflects the same relationship between gravity and energy that governs its present. During the main sequence, fusion supplies pressure against gravity. When core hydrogen ends, gravity contracts the center and ignites shell fusion. When helium becomes available at sufficient temperature, another nuclear phase begins. When no further fuel can be ignited, quantum pressure supports the remnant. At every stage, the star changes because one source of balance gives way to another. The shining cannot last forever, but it also does not end in a single failure. It becomes a long sequence of transitions, each shaped by the mass the Sun receives at birth. A heavier star would proceed toward more advanced fusion and a violent collapse. A much lighter star would consume hydrogen more slowly and never become the same kind of red giant. The sun follows the quieter path of a moderate star, expanding, shedding its outer layers, and leaving a dense ember behind. Its present light is therefore one chapter in a history that stretches from a dark cloud to a white dwarf. The hydrogen now disappearing in the core is not merely fuel being spent, it is the cause of a slow internal rearrangement that will brighten the sun, alter the planets, enlarge the star, and eventually expose its final core. Endurance carries the seed of change. The same fusion that preserves the sun also creates the helium that will bring the stable era to an end, and the same gravity that ignites the star will guide it into its final silence.